All right, what we're going to look at here in this video is going to be mapping epicenters. This is a great lab for helping your students to learn more about earthquakes, the seismic waves that come out, specifically the P and S waves, as well as surface waves. And then also figuring out, well, how do we figure out where the epicenter of an earthquake is? So you've already looked at and read these procedures on mapping epicenters. What I want to kind of talk to you about now is if we were taking this on a 5E type format, a great engage portion of this lab would be to start off with the YouTube video Killer Quake. I believe that's by Nova or National Geographic. Showing them just the very beginning, first few minutes of that really is a great hook for them. Just seeing kind of what this earthquakes do, the damage that they cause, and the waves that are coming out. And that will really get them excited about what's coming next. If you looked at your procedures, there is a part 1 and a part 2 to this lab. The very first part of part 1, after they've read the introduction, they should know a little bit more information about seismic waves, compressional waves, and transverse waves, which are our P waves and our S waves. It shows a great diagram of both of those waves right here as the P wave, okay, and right here as the S wave. And as students see these diagrams, that gets to part 1, which is allowing them the opportunity to replicate those diagrams using a slinky. So as groups, you would get them onto the floor in the hallway, somewhere like that. Maybe give them a time limit, because this is a great opportunity to say, hey, you know what they look like, you know what they are. You may not know how to create them, but you have this many minutes, maybe 5 minutes, to work as a group, come up with a plan, and to demonstrate it, make sure you can replicate it, and then I want to see you make each one. I found that this has worked really well into the classroom with the students doing it. Once they kind of get it stretched out and going for the students to do this, in order for them to get the P wave, that compressional wave, they're going to pull back and push forward, and you can see it gives kind of that compressional pushing and squeezing together and then releasing. So one more time, it's more of a push forward, pull back, and push forward. That would be the P wave. Now for the other one, which would be the transverse wave, which is the S wave, they're going to do more of a side-to-side motion, which would be more like this. And once they have their slinky stretched out, it really shows the wave moving down and back. Some great talking points on this one too is asking the students, what did you notice happened to your waves as it went down to the other student and then came back? And they'll probably talk about, well, it wasn't as strong, or it got weaker and eventually died out. And you can talk about the energy of an earthquake wave and the seismic waves and how it loses energy the further it gets from the epicenter. Because that's really going to play a role in helping them find the epicenter and realize that places farther away are going to experience less shaking, and the places that are closer are going to experience more shaking. Last little tip, have the students hold the last few parts of the slinky, and don't let them do it not on the ground, because it can easily tangle, and once the slinky gets tangled, it is extremely hard to get it back out. All right, once the students have done that engage portion where they use the slinky, when they get their actual student sheet, up here at the top for part 1 that's already labeled, they will actually go back and draw what that P wave motion looked like as well as the S wave. So this gives them an opportunity to show what they know by going back and recording that down. Once they've recorded that down, they'll move to part 2, which is a data table. And this is probably one of my favorite parts that really sticks out about this lab, is the students actually have to look at seismograph data. And they have to find and identify the P wave and the S wave and measure the difference between the arrival times. So if you come up here, I'll show you kind of an example of what we're going to have to do. The students would have this, they've already read through it, they've seen the procedures, but here's kind of the example. Notice the very first mark of the seismic wave arriving, this is your P wave. And what I tell the students is to mark it with a line, okay? And this would be something I could show them on an Elmo, something like that on the projector screen so they can see this. Then the next wave would be the S wave. So what they're going to do is they're going to measure the distance from here to here. That is the difference between the P and S wave. So they will take their ruler, they'll put it right at the 0, and they'll measure it all the way out to right here. And when we see by doing this, it actually comes out to be about 2.6, 2.7. And what I would tell the students is, let's go ahead and write that down next to the actual seismogram. Now, what I like to do in my classroom is give the students an opportunity to write this down. That way they have it. And then when they get their actual copy of the 6 seismographs they're going to use, they're going to record it there as well. But the next part of what they would have to do, now that they have already recorded this, is they're going to use this time scale. Because on their student sheet, which is right here, they have to tell us the difference in arrival in minutes for the time. Well, if this is the time scale, it's in minutes. They will take this number, which was 2.6 centimeters, and they'll come down here and they'll measure from 0 all the way out to see, here's 2.6, which would be right here. And it's right at about 1 minute, just a little bit past 1 minute. So that would be the difference in the time scale. So that would be the example. What we'll then do is the students will get a copy of Earthquake 1, Seismograph 1, Seismograph 2, Seismograph 3. It has the time scale in minutes at the bottom. It may say seconds, but it is minutes that they actually have to use. And I like to do an I do, we do, you do. So if you look here, seismograph 1, they would identify this as the P wave. Right here is the arrival of the S wave. Now, if all the groups have a copy of this for each of your classes, or maybe you put them in one of those little 1-cent sleeves, the little plastic sleeves, they could use expo markers and erase it. That way each class can actually mark on this. They can mark where the P wave arrived, the S wave arrived, and it just makes it a lot easier for them to keep up with their data and record it to their table here. So if you'll come back here, I'll show you exactly how this is going to work. So we have seismograph station 1. I come here, I put it right there on where the P wave began, and here where the S wave began. And as you can see, I'm getting about a 3.9 centimeters. So I would encourage the students to write down 3.9. And then we come down here and we're going to measure this here. And I know that I'm looking for 3.9. And if I come here, I line it with the 0, I come all the way out here and it lines up right here on this mark. And notice, here it is. So there's 1, 1.2, 1.4, 1.6, 1.8. So if I come over here to my data for a seismograph, the minutes is going to be 1.8 minutes for seismograph station 1. It's important that the students know when you measure the distance from the P to the S, that's not what's actually going here. What's actually going here is the time scale in minutes. So we'll do one more. Here's seismograph 2. The P wave arrived right here. The S wave arrived right here. I line up the 0 here all the way to this point. You can see it's right here at 7.123, 7.4. So I can record down 7.4 was my centimeters. I come down to my time scale, make sure I line up with the 0. There it is. And then I come right here, here's 7, and then 7.4 is right here. So I can look on my time scale, here it is at the 3, 3.2, 3.4. So I would come over here to my answer sheet, 3.4, and that is going to be in minutes. And then the students would work through seismograph 3, record it down for earthquake 1, and then they would have earthquake 2, which would be seismograph 4, 5, and 6. Depending on how much time you have in your class, some of my recommendations, it can be difficult at times to cover all of your standards. Maybe have one half of the class working on earthquake 1 and the other half of the class working on earthquake 2. So you can kind of demonstrate seismograph 1 and 4 for the students, and then allow them to work on the rest of them and following it. This is a great one for you to be able to move around and really help out the students. But this is the part where they have this portion done. And then now we're going to take a look at, well, how do we figure out the distance from the epicenter? Okay, now that the students have went ahead and already figured out the difference in arrival time between the P and S waves using the seismograms, what we're going to now look at is what is the distance from the epicenter. So this can be a difficult task for the students because it is involved using a P and S wave time travel curve, which is this curve right here. And so what I'm going to do is I'm going to show you how you can successfully use this. And hopefully the students feel pretty confident in being able to do this. So if you'll come on up here, I'll kind of help you out with this. This is kind of where the students should be at this right now. Is they've already started part 2. They've already figured out the difference in arrival time of the P and S wave, and they have their information answered. What you can see we did for earthquake 1, I added the 2.3. Now a little thing I like to have my students do is add this extra box out here so that it can be P to S wave distance. So when they're measuring those P and S waves, they could have just wrote their distance here and then measured on the bottom and wrote that information here. So that's a little extra thing that I like to add to it, but let me show you how this is going to be done now. So first thing that I need to do, I need a note card. A small little note card will work for each group in order to be able to use it on this curve. They're also going to need like a pencil or something to write with when it comes. Now, your students can use this one. This one's perfectly fine. What I tend to have some students that need a little bit of extra help in my classroom that would really struggle with something like this. So I've actually accommodated mine to help my students a little bit more, and I created this kind of example so that they know that, hey, this is the S wave, this is our P wave, and then I added the markings in between. I gave them measurements for each of those, and then especially over here on the side. We figured out that, okay, the first line is 0.4, 0.8, 1.2, 1.6, all the way up on our time travel. We also identified the x-axis as well as the y-axis. And then round up to the next distance if you are past a line with the halfway mark. And I'll give you an example of what that means. But this is something I do for all my students. I print it out for each group and they use this with their student data. So let's take a look. My seismograph station 1, the difference in arrival time between the P and S wave was 1.8 minutes. Well, if I come over here to my time travel curve, here's my travel time in minutes. So what we're actually going to do is I'm going to place my note card right here at the corner of the 0 zeros so I can still see this line here. I'll put a dot in the corner for 0, and then I have 1.8 from my data. So I need to come up, here's 2, and this is why it's important to mark these lines out, because I know that the line below 2 is 1.6. So if I go halfway in between, which would be this mark, and I can put a 1 next to it so that I know that's seismograph 1, I'm now ready. So what I'll do is I'll put this on the 0, and I'll start traveling up. This dot down here is my P wave because that's the first wave to arrive. This is the S wave, the number 1. So I'm going to keep traveling. I get to 250 from the epicenter. Is the S wave on the S wave line? Notice it's not. So I need to keep traveling. Now I get to 500. Now take a look. I still have my dot on the P wave, and now this is on the S wave. So therefore, the distance from the epicenter for seismograph station 1 is 500 kilometers. So I would come here and I'm going to write 500. That's my answer for number 1. Now I'm going to do one more for you. And we have 3.4 was the minutes for seismograph 2. Once again, I move my note card here to the 0. Here's 4. I come down, it's 3.6, then 3.2 for these little lines. So in between 3.2 and 3.6, right here in the middle, I would put my little mark, and then I would put a 2. I come back down here, and I start traveling up that P curve. And I can go ahead right here to where we left off last. Notice the 2 or the S wave is not there. I come up here to 750. It's still not on there. I keep traveling. I'm up to 1,000. Now notice, here at 1,000, you might have a student say, no, it's on there. But if you look, it's above it. It's not actually on there. So I need to keep going. Now notice, halfway in between 1,000 and 1,250, it's actually on here. So students would have to figure out, well, what's this point here? And here's where that actual answer would be 1,125. But I tell my students the actual answer that you'll write down, we'll round it up to the next spot, which would be 1,250. Because if you look at it, it's technically a little bit lower here, but in order for you to get the correct data, as we figured out in this lab, you actually have to round it up to the 1,250. So the distance from the epicenter, I'm gonna put 1,250 is my distance here. Even though if you had that student that just wanted to write down the other number, they could write it down in a parentheses so that they knew that it was technically 1,125. So we'll do number 3 real quickly. Notice for seismograph station 3, we have 2.3 minutes. So once again, I will put my note card right here on the zeros. Here's 2 minutes, and then here would be 2.4. I'm gonna go just underneath that. This will be my 3. And now you understand why we're putting those numbers there so that you don't get confused of which is which. I have my dot right here. I go along that P wave until I get them on the same. And notice when I get to 750, they're both on the lines here. So it's on the P wave, it's on the S wave, and so 750 kilometers would be my distance. So I will record that down here. And now we are ready for our next part of this lab, which is calculating the radius, so that when we get our seismograph map and we get our compass, we can actually draw the radius around each of our seismograph locations in order to pinpoint the epicenter. All right, now that you've completed the time curve and you've recorded all of your distances to the epicenter, now we need to calculate the radius. So coming back to this sheet right here with the time curve, you'll notice that on procedure step 3, it gives you the scale that they use in this lab in order to figure out the calculated radius. And what they tell us is this, that the scale is 1/2 centimeter equals 100 kilometers. Now I'm gonna go ahead and tell you, in my classroom, students got real confused when trying to do the formula for calculating the radius. What we wound up doing is saying, all right, so if we put 2 halves together, that makes up 1 centimeter. 1 centimeter equals 200 kilometers. So that made it a lot easier. So we use this formula here in my classroom. I encourage you to use it in yours. And it's this, distance from the epicenter number, which is going to be this number here. So the students recorded distance from the epicenter. We had 500 for seismograph station 1. So what we would do is we would then take, all right, I have size 1, it was 500, and notice for my formula, I used the scale, which is 200 kilometers equals 1 centimeter. So I put 200 underneath, I divide 500 by 200, and what I'll get is 2.5 centimeters. And I will record that calculated radius right here as 2.5 centimeters. Then I would go to my next one. And I think this is where you would find that your students, hey, in each of your groups, go ahead and calculate seismograph station 2. So what was your actual distance from the epicenter? 1,250. What are we dividing that by? 200. When we do the calculations on that one, we're going to wind up getting 6.3. And you can have them round this to the nearest tens place right here. So you get 6.3. Well, I would record that here as 6.3 centimeters. And then they could do that last one, which the answer they would get would be a 3.8. And I'm going to record it down here for our notes so that we can move to our next part. Now, once they have figured out the calculated radius using the formula that was provided, they are now ready to find the epicenter. The next page that they'll have will be this seismograph map that they'll use. Now, it's important to remind the students that when we use the seismograph map, notice that there are 6 locations. That's because there's an earthquake 1 and an earthquake 2. Depending on what you're doing in your class, you could have the groups do both earthquakes. I like in my class, based on time-wise, to have one group do earthquake 1 and other groups do earthquake 2, kind of a split up. And then they can compare and contrast what they got based on their data. So now that we have this, we're going to be using this, which is a compass. It can be difficult for the students at times, but I'm going to show you exactly how this works so that you can be successful. All right, now the students are ready to find the location of the epicenter based on the data they gathered. So let's look at the data that the students should have right now at this point. They've already figured out the difference in arrival time using the S wave and P wave difference. And they've already figured out the distance from the epicenter. And then they've calculated the radius using the scale. Now what we're going to do is take these numbers and our seismograph locations, and we're going to use our compass to create a radius around each of those seismograph locations in order to locate the epicenter. So at the beginning of this lesson, you should have read that it takes 3 locations in order to pinpoint the epicenter. So since we have 3 seismograph stations, why don't we figure out where our epicenter is located? So our first one that we have, seismograph station 1, it was 2.5 centimeters in radius. The epicenter was away from seismograph station 1. So with our compass, you'll notice this first part here. This is kind of what I call like a bullseye. If you've played darts or any type of game, you've probably seen the bullseye before. We want to get that bullseye, the little mark, right on the seismograph station 1. So I will move it to get it right there on top of it. It's easy to move, so you have to actually put your finger on top. Once it's there, the compass will actually move freely, but not move from that location. Now, the next thing that we need to do here is we had 2.5 centimeters. We want to use this piece right here, and notice the triangle. We want to take that point of the triangle here and get it to 2.5 centimeters. Now, if you have the old screw compasses, you're lucky because they probably have already broke by now. But with the new improved version, you just have to push down on this little tab here and it will allow you to move. So I'm going to push down on it and I'm going to move it to 2.5. And I want to make sure that that triangle right here, notice there's 2 here, 3. Notice how the triangle here is pointing at 2.5. I will then, if you can see this hole right here in the middle, take a pen, pencil, whatever you would like to use, with your fingers still on the bullseye, place it down in, Make sure you're on a good flat surface, and then you might have to shift just a little bit, and there it is. So what we know right now about seismograph station 1 is that 2.5 centimeters away is the epicenter. But all we know with one station is that somewhere on that circle is where the epicenter happened. Well, that's not very accurate if you're a seismologist, and you need more. So once they gather information from another seismograph station, let's see what happens next. So based on our data, seismograph station 2, it was 6.5 centimeters away. So what I'm gonna do here, just to hopefully show it a little bit easier, I'm gonna hit this. Notice here's our 2. I'm gonna slide that first little triangle. Here's 6, and we said 6.3. There's 1, 2, and 3. I'll let go. It's not moving anywhere. And now I find seismograph station 2, which is located here. I put the bullseye right on top of it. Finger is on it. Pencil goes in, or pin. And if your students have any trouble with actually doing the compass, it might be that they have a book or notebook underneath it, and that would give them trouble. Make sure that they do it on a flat surface. And now look at our seismograph location 2. Look at the radius of our circle, and we know that the epicenter is somewhere here, but it also is here. And notice that they intersect each other at these 2 points. So we now know that the epicenter of our earthquake is either here or here. We have a 50% chance of knowing, but that's still not good enough. We need to 100%. So now we move to seismograph station 3, which our data shows us was 3.8 centimeters, a 3.8 centimeter radius from the seismograph station. So here's seismograph station 3 down in Florida. And this is a great opportunity to help students realize that, earthquakes are felt all around the United States. So when it happens in one location, all of these seismograph stations located across the United States and even the world pick up the waves from that earthquake. It may not be as big, it may be smaller, but it does pick them up, and that helps them to pinpoint the epicenter. So coming back here, 3.8, I'll push down. Here's 3. I'll move that arrow to 3.5, the triangle. 6, 7, and there is 3.8. I'll place my bullseye on the seismograph station 3. Finger is gonna go on. I place it into, and then I draw my circle. And now there is my circle. And you'll notice that with this one, the point where all 3 circles touch, which is right here, that is the epicenter of our earthquake. So as long as you have 3 locations for seismograph locations, you can locate the epicenter. This is a long activity, but it's very good for allowing the students to interact, to create the seismic waves, and to build on previous knowledge all the way up to actually locating the epicenter of an earthquake. I would highly encourage doing this lab. It really gets the students interact up, moving around, problem solving, and as well as it's a lot of fun. I would highly recommend using the fist of 4 during this one, especially to gauge the classroom with an assessment just to see, hey, how is everybody doing on this portion? Is everybody good? Give me a fist of 4. So you know where you need to move to if a group is struggling. But the students would then write down where the epicenter was located. In this case, it was Virginia. And then earthquake groups 2, they could move around. They could come look and see where earthquake 2 got their epicenter and where earthquake 1, they could kind of compare and contrast. The students would then move to calculating the difference in the speed of the P and S waves. You can do that one. I don't have a lot of time to do that when I get to the point. They pretty much understood what they needed to with this. I move immediately to the conclusion questions. But that is mapping epicenters. It was a long one, I know, but I know you can handle it.